now we're going to get started with this. Ladies and gentlemen, this is a copy of a data tag that's on a furnace. It's only an example. We're going to talk about some of the data that's on here. This is off of a ring furnace. It's a 75,000 BTU furnace. And a lot of these things we don't have to go through, but it does tell you here that we want a gas supply for natural. We're going to talk about natural gas. You can't hardly see this. You almost need a magnifying glass, but I'm going to review this with you in the job site form. But it says we want 5 inches supply gas pressure, 3.5 inches regulated. But what we're going to spend time on is temperature rise. So if you look at the data tag, it says the temperature rise of the furnace will be 45 to 75 degrees. And we're going to talk about that in a little bit. We're also going to talk about the spec here that says maximum external static pressure. We can call that ESP, maximum external static pressure. And we're going to go through that in a little bit. But take a look at the numbers. It says 0.12 inches water column and 0.58 inches water column. Okay? So I want to put that on the side for right now. And let me shut the overhead off. And we're going to come back to that in a little bit. Ladies and gentlemen, keep in mind this video is intended for HVAC people with a background, and they have to know at least the basics of heating. Okay? All right. But again, it's intended so when you're on the job and you're in trouble, you know how to gather data. I'd like to go now to the next page that's in your handout. We'll put that up here. And this is a copy of the job site form. Ladies and gentlemen, let me make something clear. If you can fill out an answer, or if you can fill out the job site form and answer the questions, you'll be able to solve the problem yourself. And typically you won't have to call us. It's just a reminder for you to be able to gather the data. Let me bring this down again and let me explain something. The job site sheet, ladies and gentlemen, serves the purpose for the technician to be a guide. You can use the same information even when you're doing a PM check. But if you're in trouble, you know the category of questions that you're going to be asked. And when you call either Jeff or me or any of the Park Supply associates to give you technical information, we're going to be using a job site sheet as a reminder for us so we know what questions to ask you. Because keep in mind, we expect you to do your homework and gather data. We have to do our homework and gather the data also because if we get the manufacturer on the line, they're going to be asking the same questions. And really, they're not going to talk to us unless we have some of this information. So again, that's why we want to go through this with you and explain how to get it. Let's go back to the overhead, Jeff, and we'll look at the job site sheet, and all of this is basic information. The owner, who the customer is, who the contractor is. Most important, model number and serial number. Without that, I got to tell you, it's very difficult to help you because we don't know what we're talking about unless we know what furnace we're working on. Okay? And of course, down here, a description of the problem, actions taken to resolve the problem, and additional information. This is all information that you can fill out. But now let's talk about the questions. Look at this. We're going to be going through questions 1 through 13. And then I would like you to turn the page, ladies and gentlemen, go over to the next page. And we're going to complete this by going through questions 14 through 31. So we're going to be answering 31 questions. And we can do this in less than 20 minutes while at the job. Okay? So we're okay with that so far? All right. So that's what we want to do. Now hang in there with me. And I'm going to bring you back to, let's go back to the first page now of the job site sheet. And we're going to fill in some of these things up here. We need to do the first 4. And as we go through all of these, we'll stop and discuss some of them. Some of these are basic. But number 1, 2, 3, and 4 has to do with the temperature rise. Now, supply air temperature and return air temperature, just so we can do the math, ladies and gentlemen, I'd like to just put down a return air temperature. Let's just put down 60 degrees. How would that be? because that would be a cool house, and you could be using a setback thermostat, and we could have a 60-degree temperature rise for the return air. Okay, if that's true, Jeff, let's put in a supply air temperature that we could average on any furnace. What do you think we could put in there?
110.
110? Okay. And so if we had 110 degrees, what's the actual temperature rise as an example?
50.
And that would be what?
50.
50 degrees. Just as an example, I'm going to show you, because I'm going to surprise you with a couple of things right now. If we go back, ladies and gentlemen, to that data plate, we had a temperature rise of between 45 and 75 degrees. And if this was a furnace that we are working on, it should be warmed up between 45 and 75. So now let's go back to the page with the data, and let's put down the rated temperature rise, which is 45 to 75 degrees. So if that's true, is this furnace working okay? Is it good for the customer?
Yes.
Yeah.
As far as temperature rise, yes.
Absolutely. And see, Jeff is saying for the temperature rise it's good, and I know exactly what he's talking about. So let's talk about that. Let's go back and ask that question. In other words, we have a 50-degree temperature rise, and specification was 45 to 75. That means that that furnace is working at the lower end of the temperature rise, okay? But it's working perfect, and it'll last forever. All that furnace needs to be done. All that needs to be done to the furnace is do a PM check every year, clean it, make sure everything is proper, and it'll just work. So, is it good for the furnace? Yes. Is it good for the customer?
Yes.
Oh yeah? Let's talk about that. And that's how we conduct the class. Ladies and gentlemen, keep in mind, you may be selling this customer, and whether it's an 80 or 90 plus, it doesn't make any difference. The customer has replaced perhaps out of their home an old inefficient, 60% efficient furnace that had registers firecracker hot. And they could have had a temperature rise of 100 degrees on the old furnaces. So the point is, especially if you had an elderly couple, they would sit back in a chair and they would put their feet up on the register and they got 160 degrees coming out, even though they were using a setback thermostat, and in the morning the house is down to 60 degrees and they felt great, but they wanted to be able to come out and put their feet on there and they could warm their feet. Now we sell them a furnace that's only got 110 degrees and the furnace lasts forever, but is it good for the customer? No. They hate it. But that's the point. Ladies and gentlemen, it's good for the furnace. Sometimes we're in a category that we have to be able to maybe adjust the furnace for the customer as best as we can do it. Let's talk about that. Let's go back and look at this temperature rise. And again, we're only using this as an example. So let's see. Let's just say, for an example, let's say that this came from the factory on a heating speed, which is question 5. It came on medium-low. And if we wanted to increase the temperature rise, what do?
Slow the blower.
Lower the blower, correct. So now we could actually change it, and we could end up maybe getting a temperature rise of, let's see, what would be the highest temperature rise we could get? If it's 75, and we got 60, 60 and 75 is what, 135?
Yes.
Be 135 degrees. So we could go to medium-low, and maybe we could bring the temperature rise up. But look at it. Let's go back. Even at the highest temperature rise, 135, and that customer was used to 160. Ladies and gentlemen, I hope you understand that we have to advise our contractor that they have to explain to the customer that it's a high-efficiency furnace. Because it's high efficiency, we give up some comfort. The facts are, it's high efficiency, it does work better, got a lot of electronics, it's a cooler furnace, it conserves fuel, and the government has imposed all of these regulations on the furnace manufacturers, and we cannot buy anything really lower than a 78% furnace today. But if we have an 80 or a 90, that's the compromise. The supply temperature is going to be lower, it's normal, and that's the best we can do. I'm spending some time on this because we don't want contractors increasing gas pressure to make them hotter. That's not what we do, okay? We leave them at the specification. We can do the best we can and try and get the temperature rise as warm as we can. Is that okay? All right, so we got past those questions. Jeff, let's go back to the job site form again. So now we got past temperature rise, okay? But before we do that, I really don't want to go beyond that yet because there is a page in your handouts. If you look at page 97, and all of your pages are numbered at the bottom, and I have to find them up here as well. So hang in there with me, and I'm going to bring this one up. Okay, you should have this page. It says page 97 at the bottom. Okay?
Okay.
So remember now, when we are taking a temperature rise, we can follow the information, and this page actually comes out of a training manual. And Jeff, let me just come over here on this side, and you can zoom in on this. Ladies and gentlemen, this is the manual that I'm using. I'm using an 80-plus training manual from Rheem. And of course, we use this on the Rheem and the Rude product, and also Weather King. But this is the new updated version, and these pages actually were photographed from this manual. So this is the one we're using. We put this over here, and let's go back. So this actually is page 97 in that book. But the point is, it's talking about checking airflow and taking temperature rise, and so they're using an electronic thermometer to do this. And we put a thermometer in the return. Are you able to see that there? I don't know if you can get a close-up, but that's okay. We're putting a thermometer into return, and we're also putting one in the supply. Let me do this, Jeff. I'm going to come over here and get a thermometer, because this is not a nice tool to have. We would suggest that you do get a thermometer because, I don't know if you can see that, but that's okay if you can't. It's got digital readout. And this is what makes us good at what we do. We can use pocket thermometers with a digital readout, and it works terrific for heating because we can poke a hole in the return and stick the thermometer in there, or we can poke a hole in the supply, stick it there, and a pocket thermometer works. But you can't use the pocket thermometer when we check superheat and subcooling on air conditioning. That's the reason we would suggest that you get one of these thermometers. Again, we said that we expect you to be equipped. For heating, you could get all of these tools for probably $350 that we are showing you here today. This here is actually the most expensive instrument. These are probably around $100 a piece, and everything else is less. But again, this would be the a thermometer, any kind of an electronic thermometer. Okay? All right, let's go on. So let's talk about one more thing yet, though. If we're checking temperature for temperature rise, again, we put our probe that would be electronic, and that would be the thermometer. That's a little thermocouple probe. We can get a hole by the return. We want to check the temperature that is coming back to the furnace. So you get as close to the furnace as you can, so we see the temperature that the blower is actually pulling in from the return. On the supply, ladies and gentlemen, if you talk to several people, you're going to get several different opinions. We're going to suggest in this class that you take the probe for your supply. Here's your plenum. Let's say it's an upflow. We're going to ask you to go about 5 or 8 feet down the plenum before you put that probe in there. We want an average of that supply temperature. Now, other people that you talk to will say, well, no, you can come right over here above the A coil. Now, a lot of the books tell you not to put the thermocouple there because you get radiant heat from the heat exchanger. And I got to tell you, whenever I had a factory rep out and we would talk about this, I would put my probe down here 5 or 8 feet, and he would stick his right above the A coil, and I got to tell you, really, the temperatures were the same. But it's up to you. All we're saying is, though, get a good supply temperature wherever you feel comfortable in doing that. Okay? We're okay with that now? Mm-hmm. All right. Now we can go on then to the next topic. Let's go back, Jeff, to the operating voltage. Question number 6. When we talk about question number 6, it says the operating voltage, that's our supply line voltage, and of course our control voltage is our low voltage. Now, I prompted Jeff yesterday when we were discussing how to make this video, and I told him I would like him to give us the response that typically in a class we say, what's the voltage to the furnace? So, and I tell you what, maybe I'm not going to ask you, Jeff. I'm going to ask Kevin and Herb. And I want you to give the answer, gentlemen, that typically a contractor would give us. So if we ask a contractor for, and let me shut this off and come over here now. If we ask a contractor who's at the job for the voltage, what's the voltage to the furnace? What's apt the technician going to tell us? It's how much?
115 volt.
Absolutely, be 115 volts or 120 volts. And at that point, ladies and gentlemen, we're going to tell the technician, would you please go back and check the voltage, because we know that he hasn't checked it. Let's come over here, Jeff, with the camera a minute, and let's take a look. Ladies and gentlemen, today we have digital voltmeters. We have digital voltmeters that give you large displays with a decimal. There's all kinds of voltmeters. You can buy a voltmeter for $50, $65 or $700. It doesn't make any difference. They all do a nice job. The cheaper meter is just a little bit slower. But what we're asking you for is we want a decimal. So if you were to give us a decimal of a voltage that's actually good, we're going to say, okay, that means you checked it. So Kevin, what do you think would be a good voltage for a furnace somewhere between 150 and 120 with a decimal?
118.6.
118.6. Let's do it. Let's come back over here. And let's put down operating voltage is 118.6. And then we would say to you, terrific, you did a great job. You checked the voltage. By the way, we would like you to check the voltage with the blower motor running, because that would be the maximum load, okay? So we got 118.6. Now, gentlemen, ladies and gentlemen, if it's the control voltage that's being supplied by 118.6, we just may have a transformer that is 120 volt, it would be a 24 volt transformer with 120 volt supply. So we got a little bit less than 120 volt. So we would expect then that our low voltage would be a little bit less than 24, just a little bit. So Herb, what do you think we could put down for a little bit less than 24 with a decimal?
22.9.
Perfect. Ooh, 22.9. So it all relates. And ladies and gentlemen, let me make something else clear. Let's talk a little bit. If you're in trouble, you may not have to respond to all these 31 questions. We're only going to ask you to respond to the ones that are important to your problem. So the ones that pertain to the issue, those are the ones that we're going to be asking you for. But again, how long does it take you to check the voltage, okay? All right. Now let's talk about the current draw at the thermostat. And number 8, the anticipator setting. Ladies and gentlemen, I'm not going to spend a lot of time on this one, but only to tell you that if you were using a manual, let's shut this off and talk a little bit. If you were using, and the reason I'm saying that is because Jeff has got to follow me with the camera all the time, but we're doing fine with that. If you're using a mechanical thermostat, it comes from the factory preset at 0.4 amps. And it's designed to be moved. You have to take a current draw of what that thermostat is controlling. We no longer have thermostats controlling gas valves. They turn a board on. The board turns everything else on. So it's the current draw of the integrated circuit, the board. The ring furnaces typically are all very low current, 0.1 amps. So even if you don't check the heat anticipation, please set your heat anticipation for 0.1 if you have a mechanical thermostat. So now we can come back here, and let's just say that the current draw at the thermostat would be 0.1, and if that's true, we want number 8 to be the same, and that would be 0.1 amps, okay? Now, let's talk about that again. We know that the heat anticipation on a digital thermostat, the instructions have to be followed. There's many different digital thermostats. We don't have to set any levers, but you do have to follow the instructions. Okay, some are preset, some are not. You have to be able to program them. But if it's mechanical, please set that down. I have to tell you, we had a contractor where we did a live class for him, and we actually had him check the heat anticipation. And he says, well, no wonder I'm having trouble with all of these mechanical thermostats. He says, I know that they all come preset at 0.4, and he says, and I know that you said that it was supposed to be 0.1, and he says, now I see on the amp meter, it is 0.1. He says, but I was turning them all up to 1. See, so there's a big difference from 0.1 to 1, and he kept warranting the thermostats. And they still didn't work, so he went to electronic ones, and of course, and they worked fine. So at that point, now we understand about the low amperage for heat anticipation, okay? All right. Again, ladies and gentlemen, everything I'm going through, and I talk fast, and the pace is very quick, but all of this information is in the training manual too. You can educate yourself with a training manual. Let's go on. Let's get to the next two, which are exciting. I love this part. It says, is the polarity correct? And of course now, Jeff, let's say Jeff is the technician out there, and we're going to say to him, Jeff, is your polarity correct? And you would respond?
Yes.
Yes, of course. very, very simple. So let's put down yes. All right. Now let's say, and then we'll say to Jeff, he's just going to answer one answer. Is it grounded according to code? And you're going to say?
Yes.
Yes. And now we talk. Because, is it grounded according to code? Let's talk about this. Remember, we're making this videotape at one of our Chicago branches, and it's one of the Chicago suburbs, Elgin, Illinois. And this videotape is going to be used at all of our Chicago branches, all of our Southern Indiana district branches, and I got to tell you, our videotapes end up going around the world. It amazes me the countries that find our videotapes on a website. And so this actually goes around the world. So what applies in Chicago, ladies and gentlemen, does not apply anywhere else. And let me explain. Is it grounded according to code? Well, if the manufacturer's rep came out to look at a furnace, one of the things that he would do would be to go to the junction box. We know that in Chicago, we use conduit that comes down, and we have two wires inside the conduit. We have a black wire, which is hot, and the white wire, which is neutral. And of course, that's how we check our polarity. We put the voltmeter on the black, touch the ground, which is the conduit, and if we get a voltage reading, we know that our polarity is correct. But the black wire then is connected to the black wire in the junction box of the furnace. The white wire is connected to the white wire in the junction box of the furnace. And then the manufacturer's rep will be there, and he opens up the box and he says, okay, black wire to black wire, that's good. White wire to white wire, that's good. And he says, that green wire. He says, I'm going to go and pull it out. And he pulls it out of the conduit, and there it is. It's hanging there. It's just a little piece of green wire hanging there. And he says, He says, now I know your problem. And that's because the green wire is not connected to the to another wire. And I said, well, this is Chicago. We don't have to connect the green wire to anything else. Our technicians like to take the green wire and they like to hide it in the conduit. And we tell them if that's what they like to do, that's okay too. Not a problem in Chicago. Let me explain. In some of our classes, we'll tell the technician, check your voltage, check your polarity, and make sure it's grounded. Because you see, ladies and gentlemen, in Chicago, our ground is the conduit. We actually tell the technician, if he feels like it, take the little green wire out, and instead of hiding it, or even connecting it to something in the junction box, take a pair of side cutters and cut it off and throw it away. We don't need it in Chicago, and that's code. Because, ladies and gentlemen, again, our ground is conduit. And as long as the conduit is intact and it's a good ground, that is a good ground. However, what we now know today is that Chicago and the surrounding suburbs is the only area in the entire United States that uses conduit for residential outlet to outlet. Now, we know that conduit is used in other areas for other reasons in residential, but I'm saying to you that in other areas who do not use conduit, they use Romex. So Romex, of course, is the plastic shielded cable. You have the black wire, you got the white wire, and now you have the bare copper wire, which is the ground. Ladies and gentlemen, that's what the green wire is designed for. It's there for you to wire nut. If you're using Romex, you're supposed to wire nut it to the middle ground wire, which is copper. So I think we've made that clear now. In Chicago, we use conduit. That's perfectly okay to get rid of the green wire because it's functionless. We don't use it. But if you're using Romex, of course, you have to connect that. In all cases, though, we tell the contractor, if you think there's any electronic problem with flame sensing, something's intermittent, shoot, run a separate green wire from a sheet metal screw over to a water pipe, as long as there's no plastic in there, and you've also got another ground there. So you can't have too many grounds. But I hope we've explained that in Chicago, we do not need the ground wire attached to anything. Gentlemen, any questions on that at this point? Are we okay with that? We okay? All right. So, is it grounded according to code number 10? Absolutely yes, and that is correct. Okay? All right. Now, I want to go to Question 11, because it talks about combustion air openings. Now remember, combustion air is the air that the furnace uses for fire. You have to have fuel, you have to have air, and you have to have ignition in order to have a fire. But where are the combustion openings come from? All we're asking you to do is to be able to explain that. If you have the furnace in a closet, maybe you've got pipes coming down. Maybe you've got holes from the crawl space. Maybe you've got a hole in the side of the wall. Or you might be in the middle of the basement. And you might be using the house for combustion air. It doesn't make any difference. All we want to know is where is the combustion air coming from. So when we ask you that question, if you call me or Jeff, we're going to say, where's your combustion air source? So let's make this simple, gentlemen. Let's just say, for example, we have an 80-plus furnace sitting in the middle of the basement, all right? And let's just put down house, huh? Let's just say the combustion air source is the house. And of course, you may have to explain that verbally or something too. So combustion air openings would be the middle of the basement, and the air source is house. It's just a sample of what you might use. However, let's talk a little bit more. If you have combustion air, let's say you do have the 80 plus sitting in the middle of the basement and you're using the house for combustion air. What happens when it gets 20 below zero? And you may have a house that's nice and tight. And the stairs going upstairs to the first floor, you may have shut the door. And maybe there's no opening under the door. And you may have gone to the hardware store and purchase some plastic and put it around your basement windows so you don't get any drafts. And at 20 below zero, in Chicago we get down to 20 below zero. In other places even get colder than that. But the point is, if the furnace is sized right at the design temperature, that furnace runs 24 hours a day. So even when it gets below the design temperature, it's going to run 24 hours a day. And if you look at all the charts in cubic feet of air, and cubic feet of gas, and combustion, overnight you could use up a couple of housefuls of air. And so the point is, the furnace could run out of air in the middle of the basement with the windows sealed with plastic, with the door closed and no opening, and you could run out of air. You could end up having spillage, and you've got roll-out because you've got air coming down the vent. Well, that would be an inducer, but you could end up having to come out of your water heater. All kinds of things that can happen. So the point is, drafts in the house could be good. Now, all we're saying, though, is you have to be able to explain where the combustion air source. And by the way, a typical example is the furnace goes out at 2 o'clock in the morning. It's 20 below zero, very cold. People are sick in the house, so they don't go outside and they don't open up the door to introduce more air into the house. Furnace goes out, flames back up, roll-out switches kick out. Technician comes at 6 o'clock in the morning. He opens up the front door. All kinds of air comes in. Opens up the basement door. More air comes in. And he's got all kinds of air in the basement, lights the furnace, and there's nothing wrong. It's only because the house ran out of air during the middle of the night. Okay? All right. So that's enough of that. And let's go back now to the... So question 11 and 12, be able to explain where the combustion air comes from. Okay? Okay. Let's go over to 13, duct size. Now, ladies and gentlemen, if you've been to my classes before, you know that my background is service, not an installer. And if you had a 75,000 BTU furnace, we need to be able to put the supply and the returns duct size. You need to be able to talk about them. You may have to talk about the extended plenum and what the size is and how many takeoffs there are. But Jeff, you would be better at this than me. What could I put down just on a form here for a return duct?
8 by 20.
An 8 by what?
20.
20? All right, let's just put that down. 8 by 20.
And then a 10
in
by...
a supply plenum?
10 by 20, or supply plenum, that would be the furnace size, but 10 by 20 for the branch lead.
Okay, so the supply, we want to put down 10 by 20 branch,
Sure.
or
For the
extended
branch.
plenum?
Yes.
Okay, that's fine. And again, it really doesn't make any difference. The point is you still have to be able to explain it. And in some cases, your supplies and your returns are the same. In some cases, the returns are bigger than the supplies. Okay? Let's just talk about that a little bit. All we're saying to you is that a major cause of technical problems is ductwork. I just can't tell you how many job sites we have gone on with brand new furnace installations, very luxurious mansion-type homes, multiple furnaces, all kinds of ductwork, and the ductwork is inadequate, furnaces overheat, heat exchangers crack, and so forth. This is the reason we have to be able to describe the ductwork. You may have to draw it out. You may have to fax it to us. We may have to discuss that. Okay? And in some cases, we may have to fax it to the manufacturer. But again, we got to talk about ductwork. Okay? All right, so let's go back here to the overhead. And so at this point here, look at this, ladies and gentlemen. We have answered questions 1 through 13. Okay? Oh, by the way, when you do a temperature rise, I want to make something very clear. Let me shut this off and we'll talk here real quick. When you do a temperature rise, that furnace must run for 15 minutes and not limit one time. That 15-minute run time is part of your 20-minute diagnostics. Because while you're heating it up or whatever you're doing, you're checking gas pressure, you're checking flame sensing, you're cycling the gas valve, and so forth. So again, I hope I've made that clear that it cannot limit one time. Otherwise, we have an overheating furnace. Okay, let's go on. Let's go back now to the job site, and let's talk about question number 14. Question 14 would be the gas type. Let's just put down for this example natural gas. In some areas, of course, they use LP. We're going to talk about line pressure and manifold pressure, 15 and 16. I would like you to go to your handout, and we should be able to go to page 93 and 94. So let's go and pick those up. 93 and 94. Okay, here we go. 93 and 94. On 93, it says for supply gas pressure. Here we go. Supply gas measurement. Gas pressure should be 5 to 10.5 inches water column. So what we're telling you, gentlemen, is that the minimum is 5 inches water column. If you're working with LP, of course, the minimum is 11 inches. But the page there tells you that we want a minimum for natural gas of 5 inches. Typically, you're going to end up at 5, 6, 7, 8. That's about it. Okay? Let's go to page 94. Page 94, it says, let's do the regulated portion. Manifold gas pressure, 3.5 inches. I'd like you to make a note if you want on your handout. It's 3.5 inches plus or minus 0.2. And that tells us that the manifold gas pressure regulated could be 3.3 to 3.7. Huh? Let's talk about gas pressure. All right, let's get rid of some of this. And this. And let's talk here. We expect you to be equipped with some kind of an instrument to check gas pressure. You could use a magnehelic gauge. We're going to be using a magnehelic gauge and showing this to you in a little bit. But a magnehelic gauge, this particular one only goes from 0 to 3 inches water column. We use this for pressure switches and other things. But we can have magnehelic gauges that go from 0 to 15 inches, which is nice for checking furnaces. We can also go from 0 to 30 inches. This is a Dwyer magnehelic. It's very sensitive, very accurate. Sometimes technicians have the little small gauges. I think Richie makes some of those, and those are fine, but they go from 0 to 35, and they're harder to read, but they're fine. Again, it depends on what you're used to. By the way, magnehelic gauges also go from 0 to 3. We can have 0 to 2 inches. Huh? We can have 0 to 1 inch all the way, needle deflection. That's not in a handout. I'm just going through the magnehelic here. We can go from 0 to 0.5, very sensitive. And we can also go from 0 to 0.25, and that would be a draft gauge. But the point is, you could use a magnehelic gauge for checking gas pressure. Okay? Let's show you another method. You can take a slack tube manometer made by Dwyer. It's got green-colored water. It is not antifreeze, ladies and gentlemen. We check gas pressure in inches of water column, not in inches of antifreeze. So green-colored water does evaporate out of the plastic. Okay? It's a nice instrument, very accurate. All right? But when we ask the technician, what's the gas pressure, And a technician may say, well, I don't have a gauge. We say, well, why do you need a gauge? Teach them how to make one over the phone. You can make a magnet gauge, gentlemen, ladies and gentlemen. Let's talk about that. Let me come over here on this side and just very briefly explain how to make a magnet gauge. You take a piece of copper tubing. And on the copper tubing, you take something to etch some marks in here. You can take a permanent marker and etch 1/4 inch increments. So with a 1/4, half, 3/4, 1, 1 1/4, 1 1/2, 1 3/4, 2, all the way up. Maybe you might want to go up to 7 or 8 inches if you're doing natural gas. All right. So at that point, now you got all these increments. You can even take a little hacksaw blade or some kind of a scribe and scribe the marks in here. Take the copper tubing in a nice tall glass of water and take the copper tubing and put it all the way down in the glass of water, submerged. Now hook it to your supply or hook it to your regulator on the gas valve and turn the furnace on. Because, ladies and gentlemen, the gas pressure is pushing a column of water. And if we're sitting in a glass of water, you can't be more accurate than that. We're pushing a column of water. Now, how do you check the gas pressure? While the furnace is running, you start raising up the copper tubing, and you get your eyeballs right level with the bottom of that copper tubing. And you keep raising it, raising it, raising it, just until you see the bubble starting to form. As soon as you see the bubble starting to form, because you know that if you went too high, the bubble then comes out. So you just raise it up until the bubble is just starting to form, and then you look at the water level on your marks. And that would be the quantity of inches of water column that the gas pressure is moving, okay? Again, it's a homemade magnet gauge. It's as perfect and as accurate as you can be, okay? Any questions on that, how to make one out of a piece of copper tubing? So we've done that many times on the phone. Teach a technician how to make it out of copper tubing, okay? If you use an LP, you got an 11-inch one, now you got to use a nice long bottle and a long piece of copper tubing then for that, okay?
How does the pressure get into the copper tubing?
Well, right, that's a very good question. The copper tubing is here. The hose goes from the copper tubing over to the gas valve. Turn the furnace on. Now the gas pressure comes back through the hose to the copper tubing and is pushing down on the column of water, on the glass of water. Okay? It's just a method. Yes, a much more professional method is a magnet gauge or a slack tube manometer. Ritchie, I think, also makes a great little water gauge. There's all kinds, but you have to have something to check the gas pressure. Because when you're in trouble and you call any one of our park branches, we're going to ask you, what's the gas pressure? What's the supply gas pressure? And what's the regulated gas pressure? Let's talk about what we do to take it. When we check gas pressure, let me make this clear. Everything that is gas-fired in the home must be on. Water heater, gas dryer, if it's gas range, 4 burners and an oven, okay, and that would be typical. However, again, you can follow whatever policy you want, but in classes we advise the technician to keep their hands in their pocket. We say, Mr. Jones, we have to have the gas dryer turned on. So I have to have everything in the house turned on. So would you please turn your gas dryer on? And I'm only telling you that, ladies and gentlemen, because if you touch that dryer and the knob falls off, or if the gas dryer don't work, you're buying a new gas dryer. The same thing happens with the gas range. Mrs. Jones, would you please turn on all the 4 burners and the oven? And you have to stand by the range because that's a lot of heat coming out, but we have to have all of it on. And then now we go back to Mr. Jones and the water heater, because, ladies and gentlemen, we could have the furnace on, let's say at Thanksgiving Day, and the customer is using all 4 burners and the oven. They're drying clothes and they're taking a shower. Different people doing different things, but the point is they're taking a shower. That means the water heater's on. So, Mr. Jones, we have to have the water heater turned on. Now, guaranteed, if you touch that thermostat and turn that water heater on, something's apt to happen to the water heater and you'll be buying a water heater. Mr. Jones, would you turn on the faucet on the tub until the water heater comes on? This is the way we do it. You're not liable if your hands are in your pocket and Mr. and Mrs. Jones are turning everything on. If you also touch that faucet in the tub is apt to fall. A tub, faucet, drops on the porcelain, now you bought a faucet and a tub repair or something. Ladies and gentlemen, take it from the person that all of these things have happened to. So today, we advise you keep your hands in your pocket and you let the customer turn everything on. Are we okay with that? Once it's on, you check your supply gas pressure. I'm going to bring you back over here, Jeff. Again, we talked about the instrument to use. You can take a piece of copper tubing, this is aluminum tubing, and you put some pipe dope on it. And you can check your supply. You don't have to take the little valve out of the gas valve to check your supply. You can go right to the drip leg, hoping that there is one there, take the cap off, and take the copper tubing, put your hose on it, run it over to the gas valve, but take the tubing with the pipe dope and just right up in the hole, and it'll sit there, and that's how you can check your supply gas pressure. So you can check that, and then of course your regulated gas pressure, you would check on the little valve, and you have to put the little fitting on the valve for regulated. We're only giving you some shortcuts, okay? All right, questions on that? Okay. Are we okay so far?
Right.
Isn't that good stuff, huh? All right. So, let's say now, all right, Jeff, we'll let you line pressure minimum 5 inches and regulated 3.5 plus or minus 0.2, and if you checked it and if it was good, what would be a good supply gas pressure?
6.
6 inches, and now even if he wanted to use a decimal, he could, but he's saying 6. Manifold gas pressure?
3.4.
Perfect, I love it. 3.4, okay? You know, we often talk at class, you know, should we check every furnace and check gas pressures? And ladies and gentlemen, I can only tell you, you know, the people that are viewing this video typically would be technicians. You must do what the owners of your company want you to do. But keep in mind that with experience, a technician would know what very high gas pressure is like, what very low gas pressure is like. And typically, most furnaces are not checked. We have a lot of installs in brand new housing, and typically the gas pressures are not checked. Things change and so forth. But I got to tell you, it really doesn't make any difference where the gas pressure is, because if it's very bad, that furnace is not going to work. If it's too low, it goes off on flame sensing, and if it's too high, it rolls out and it kicks off on the rollout switch. So the point is, make a determination. If you got bad gas pressure, yes, absolutely check it. We're not telling you to check each and every furnace, but when you're in trouble, we're telling you that you have to check it, put it on the job site sheet, because Park Supply, PC, Pamico, Jeff, Phil Candela are going to ask you what the gas pressure is. Okay? Is that clear? Okay, let's go on. Orifice size, question number 17. We're really not going to do that because we're going to say it's not applicable. NA. The only time that's going to happen is if a customer is going to, or a contractor is going to change the orifice trying to make the furnace bigger or smaller. And we don't do that. Now you got to get into clocking a gas meter, and I got to tell you, in my entire career, I've only had one of those, so it doesn't happen. If we suspect it, yes, we'll have to check it.
If a contractor does make the orifice bigger by his own means, does that do anything to the warranty of the furnace?
Excellent question. So if the contractor increases the size, he wants to make the furnace bigger, or let's even say make the furnace smaller. Either way, if he missized the furnace, we tell you that you have to change the furnace. But if he missized the furnace and he increases or decreases the orifice, how does it affect the warranty? It don't matter anymore. The furnace ain't going to work. That's what's going to happen. Oh, I suppose if he downsized it a little bit and brought his, if he brought his gas pressure down, maybe it won't create a problem with flame sensing. But it's a very good question about warranty. Because, ladies and gentlemen, keep in mind, the people that are viewing this right now are Pamico associates and Pamico customers. We're going to tell you that Pamico Park Supply, PC Supply branches have a responsibility that if we suspect that a contractor has altered the furnace, and we'll know that by the quantity of warranty parts on that furnace, we have a responsibility not to honor the warranty. It's an excellent question. So if they alter it, we go through this a lot. We go through this where we have overheating furnaces and they change limits. Yes, they are altering it. The manufacturer won't have a problem. They'll always honor that. But it's the liability behind it from the distributor. So a counter person or a branch manager could make a decision not to honor it if he knows that it's been altered. But the furnaces, for the most part, won't operate if you alter them. But you could tweak them a little bit out of the area where they still might operate and still create problems. Okay, so I hope that answers your question enough, huh? Well, let's go on, ladies and gentlemen. Let's go now to vent pressure differential. We use this term because on the older furnaces we had a differential, but really this is the negative pressure from the pressure switches. We're going to ask you for the negative pressure. And by the way, ladies and gentlemen, this is how we distinguish who the technician is and who the homeowner is. This is how we can recognize this. When we ask somebody about the negative pressure, if they say, "What's that?" we know that they don't know heating. Negative pressure is what the pressure switches sense. They sense negative pressure, okay? We're going to review this real quick, and I would like you to turn in your handout, ladies and gentlemen, to page number 87. 87. Okay? Now, here's a picture of a pressure switch. And I would like you to look up here where it says negative pressure switches, and I'm going to read this paragraph with you. Because right now, in just a few minutes, we're going to educate you about how a pressure switch works, why we check it, and how we check it, okay? Operation. All models of the low-profile furnace use a negative pressure switch. It checks for proper operation of the induced draft blower in a blocked vent condition. The induced draft blower causes a negative pressure in the inducer housing, which closes the pressure switch contacts. Now I want to stop there and say that what we just read you should understand very thoroughly. All we're telling you is how it works and what it's for. It's a safety switch. But the next sentence is very important. It says the induced draft blower must generate a negative pressure of at least 0.1 inches below the switch setting. And we're going to stop there. We're not going to read any more, and I'm going to explain that to you. All we're saying is that the inducer must produce a 1/10-inch negative better. Now, before we go any further, we have a chart here. This is an 80-plus furnace book. These are sizes of the 80-plus furnace from 45,000 to 150. And I'm going to ask Kevin, I'd like you to pick out any one of those furnaces that you want us to use for an example.
100,000.
100,000 BTU. So we come down to 100,000 BTU, and the specification on that switch, it says the switch setting would be a 0.30. So a negative 0.30. Excuse me, that's a negative reading. It says the maximum make point would be a 0.42. So isn't 0.42 like a 1/10 better than 0.3 negative? Okay, let's shut this off and let's say, what the heck are we talking about, right? Okay, we'll give you a fast class on how pressure switches work. Remember that the, I'm going to come over here to the tool. Remember that the paragraph said that the inducer must produce a 1/10 of an inch negative more than what the switch setting is. So the point is, if you look at a pressure switch, it's stamped right on there what the specification is. The furnace that you picked had a specification of 0.3. That's negative. We're going to use a magnehelic gauge to check the switch. Now on a magnehelic gauge, again, this one here goes from 0 to 3 inches. It's a nice switch because we can use it for multiple things for heating. If we have there's a top port and a bottom port. Top port is positive, bottom port is negative. So if I take the hose, and if this is the top port, if I was checking anything positive, I could go, I don't know if you can see that on the camera. I'm making the needle move because it's positive, okay? So I'm blowing in the hose, right? So it moves, okay? Well, if I take that same hose and put it into the negative, if I blow on it again, it goes the opposite way. So negative, let's see if I can make a negative like a Venturi. You have to tell me if it's moving, is it? Is it moving?
Mm-hmm. Yes.
Okay, so I'm inhaling and I'm creating a negative, so the dial, the indicator also moves negative. So when we take a T and tee it into the hose on the negative, this needle is going to move because it's negative pressure. Is that okay? All right, so now we know how to set this up. Let's talk a little more. The paragraph said that the inducer must be strong enough to at least be 1/10 of a negative more in order to close the switch. So let's use this as an example. Let's say this is the contact of your negative pressure switch and it's stamped 0.3. As soon as we turn on the inducer and we've teed it into the hose and put a T in there, and we're looking at the magnehelic gauge, and we watch it, and the inducer comes up, we go up to, see, 0, let me back up, Here's the magnehelic, and this is how you read it. 0.1, now maybe you can get a close-up on this, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1 inch. Okay? So you get increments in 1/10 of an inch. So we can read 0.3, 0.4, 0.5, right? Okay. So as the put this here, as the inducer is on and we watch it and the switch is open, we read 0.1, 0.2, negative, 0.3, 0.4, and it closes. 0.5, 0.6, 0.7, and it could go all the way up to 1 inch above it. So let's say it goes all the way up to 1 inch. So now it sits there and the furnace is operating and it's at 1 inch. We got terrific venting, okay? Now the furnace shuts down. And if we looked at the magnehelic gauge, it would say 1 inch, 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.29, boom, and it opens up. So it's got to go below the set point to open, but it's got to be 1/10 negative better to close. Is that clear? Boy, if you know how negative pressure works and these switches work, you can check a pressure switch in moments. How long does it take for the inducer to come up to speed? Tee it in, flip your switch, call for heat, the inducer comes on, and in 3 seconds you've got your negative reading. So the only question about checking a negative pressure is, from a technician, is I don't have one of those instruments. I don't know what these cost. They might cost $75. It's an instrument that you absolutely have to have. Okay? So is that clear now how the pressure switches work? Okay. And again, if you're not real clear, you can reread that paragraph and let's go on. So, if this pressure switch was 0.3 and we need to answer question number 18, and if you could go even up to 1 inch over, and by the way, you want to be at least 2/10 over for it to work, all right? Give me a good reading. Herb, what do you think? In other words, it's got to be better than 0.3, and I'd like you to tell me something better than 0.5. And you've checked it.
I'd say about a 0.6.
0.6? That'll be fine. How about, can you read the needle in between the lines? Could you say, how about 0.65? How would that be? And then we really know you checked it. Okay. Okay, 0.65. And that's just a reading that we're going to be putting in there, okay? All right. Ladies and gentlemen, you okay with that so far? Let's take a look now at vent temperature. I would like you to turn to page... You got page 98?
Yes.
Okay. Page 98, this is an 80-plus furnace. We're going to tell you on this page, we want the vent temperature today. We never did this years ago. We want the vent temperature. Here's your specification right there, 320 to 410. Okay? We're telling you to poke a hole in the B vent. Stick a hole in the B vent and stick your thermometer in there, and after your 15-minute runtime, while you're checking your temperature rise, you check your vent temperature. And it should be between 320 and 410. And by the way, you could make a footnote there if you're working on a 90-plus furnace. That particular vent temperature will be 100 to 125 degrees. Now you have the two specifications for furnaces. Okay? Let's talk about that a little bit. When we check vent temperature, gentlemen, we're telling you to poke a hole in the vent, right by the furnace. Now, if it's an 80-plus furnace, now you got a hole in the vent. What do? Leave it alone. Remember, B vent is used for negative draft. An 80 plus furnace has an inducer. We pull through the heat exchanger and we relight, just light up the vent. The vent is still negative. It's a little less negative than the heat exchanger, but the vent is negative. A 90 plus furnace, we glue PVC together. That's positive pressure, okay? So that's positive pressure. So in a 90 plus furnace, we pull through the heat exchanger and a lot. Now that becomes positive. So if we drill a hole in the PVC pipe for 90 plus furnace, we put a screw back in that hole with RTV. So at that point, we're saying that if you want to put a screw back in the B vent, you can to maybe make it look nicer, but it's not necessary because if it's negative, that little that little hole is just part of your B vent. It's like a little I don't know if I want to call it a draft diverter, but it's negative. Air goes up the hole. It goes up the seams. Goes up the seams on the B vent. We did this class for a contractor who's been installing a lot of new housing, and for whatever reason, he never knew that an 80 plus was negative draft. And so for that reason, he wasn't even following the rules. You're supposed to use B vent, not single wall. But he was putting single wall together and putting some kind of adhesive in there to seal them. I said, why are you sealing it? We're going to tell you to poke a hole. He says, well, because combustion products will be coming out of the seams. I said, no, this is an 80 plus furnace. So a 78 and an 80 plus are all negative. The chimney's negative. The vent from the furnaces all the way up is negative draft. Okay? All right. So, if your specification then is on the 80 plus furnace 320 to 410, I'm going to tell you that this will relate to your temperature rise. So 320 is the lowest, 410 is the hottest. If you go below 320, ladies and gentlemen, you will condense in that heat exchanger. You don't want to condense in the heat exchanger. Okay, so if that's true, vent temperature, let's go back. Remember the example before we changed it? We had a 50-degree temperature rise, and the spec was 45 to 75, so we're very close to the low end. So I hope you understand that your vent temperature could be, well, 330, 340, maybe 350. It's at the lower end. Jeff, give me some kind of a reading in that category for vent temperature.
345.
345 degrees. Okay? Very good. Phew. Okay, we're doing good. Take a look at question, any questions on this so far? We okay? All right. Let's take a look at question 20 and question 21. Carbon monoxide and carbon dioxide. And let's shut this off. Remember that job site can also be used for oil furnaces. So I'm going to tell you right now that you can put NA in both of those because neither one will apply. We do not have to check for carbon dioxide in the furnace. We do that with oil furnaces. The factory rep might check for carbon dioxide if he has to make a change in the field that's authorized by the manufacturer. But we are not going to ask you to check for carbon dioxide. We're also not going to ask you to check for carbon monoxide. That's not part of what this job site is. The fact is, all furnaces produce carbon monoxide. You could be as low as 13 parts per million, you could be as high as 250 parts per million. It makes no difference, as long as that carbon monoxide goes out the vent. A good, clean, operating natural gas furnace will not create soot. If you got soot, you got a problem, and you have to resolve it. But we have no carbon monoxide that we have to check. Now, carbon monoxide, though, is part of our business today. And it's a good part of the business. If the customer says, you're coming out on your annual clean and check for my furnace, would you also check for carbon monoxide? That's a terrific part of the business. You take your carbon monoxide tester, you zero it outside, and then you walk inside the house. If you got carbon monoxide readings, go and find it. Go over to the register where the furnace is and see if the furnace is producing carbon monoxide. But the point is, we're not asking you to take a carbon monoxide tester and stick it into the flue of a furnace to check for carbon monoxide. Okay? So, let's go back and let's say that question number 20 is NA. And question 21 is NA. Now, what's interesting is the next questions that we have just looking for a red pen, so we don't have that. All right. Question 22 through 26 are all 90 plus related. That has to do with the venting. And ladies and gentlemen, I'm not going to spend the time right now going through all of this, but what we're asking you for here is to describe the venting if it's a 90 plus. We're going to ask you about the length. Is the drain vented? Is there a drain tee installed? Are you using a concentric? How many elbows? How long is it? What's the termination? So all of these are questions that we will be asking you about 90 plus. Let me back up here a little bit. Venting is a big problem with 90 plus. I can't tell you how many problems we have, and when we talk about it with the contractor, it turns out that we have sags, and we got water, or we got too many elbows. We're making this particular videotape on a day where I ended up getting a technical message in my computer this morning from one of our people that was asking that the contractor is insisting that he cannot install the furnace unless he uses 10 elbows. Well, you can't use 10 elbows. 6 are maximum. You can't use 10. So he wants to know if he can install it. Of course not. We've also had questions from contractors that say, well, I don't want to use 3 inches because I'm going way beyond the chart. Can I use 4-inch PVC? No, it's not on the chart. No, maybe it'll work and maybe it won't, but you have to follow the rules and follow the guidelines in order for us to help you if there's a problem. Nobody's there to help you if you re-engineer something, okay? All right, so we're not going to work on these right now because we're talking about an 80 plus furnace. But now let's go over to number 27 and 28. We're going to talk about microamps. We have to know what the microamps are. Now, many times we'll ask a technician, what are the microamps? And a technician says they're okay. Well, no, what does okay mean? How can you check microamps? You need an instrument. Gentlemen, I want to make something clear. Let me go back to the toolbox here and tell you that most digital voltmeters, and this happens to be an inexpensive one that we use here, but most digital voltmeters have microamp scales. So you have to have a microamp scale. You have to hook it up the right way, you have to put it on the right scale. And you know, it takes you seconds to check microamps. I hope you understand that we have a flame rod. As a matter of fact, let's go to a picture here, it's up here. You got page 70 in your handout?
Yes.
Here's the flame rod, okay? And it's showing you a picture of how it is in a burner. Let's read a little bit of this. It says here, we're going to read this paragraph right here, okay? It says the flame sense current is dependent on the control board, the contact area of the flame on the sensing rod, the burner surface, and the chassis, cabinet ground, patch between the burner and control board. Typical flame sense current is 2 to 4 DC. Understand that, please. It's DC microamps. But it can be as high as 7 microamps. The IFC, which is the control board, the IFC should hold the gas valve on line with the flame sensing currents as low as 0.5 DC microamps. Let's stop now and talk about that. That paragraph was incorrect. Today's boards, I got to tell you, they're talking about keeping the flame on down to 0.2, 0.2 of a microamp. First of all, we have a flame rod. And just a quick review, if we have a flame rod and we have a burner at the bottom, when we have ignition, we have fire that goes up and connects the flame rod. Well, if we put 24 volts on the flame rod, we actually have an AC 24 volts available on the flame rod, which is the flame sensor. We have the burner down here, and once we have fire, the fire becomes a conductor for the flame rod. So between the 24 volts and the burner ground, and the ground is the gigantic ground, which is the furnace and goes back to the conduit or the Romex wire, but that's a gigantic ground and a very teeny tiny tip on the flame rod. So if we put 24 volts, we have AC. When we use this as a conductor, when the fire conducts current, it converts it to DC. So it's not AC microamps, it's DC microamps. And I got to tell you that if you look on a scope, this is really neat. Remember, this is AC, And we know what a battery DC is, straight line. And we know what a pulsating DC is. We can pulsate, everything is above the line or everything is below the line. And the more that are below the line, let's say that's a very filtered DC. Well, the DC that the electronic board sees is the flame rod here, burner here, fire here. It's converted to DC. If you just take the line and start coming down, the DC on a scope looks like this. It comes down and it goes back up, and it hardly makes it back up, and then it drops back down. It even backs up a little bit. Then it comes back over here, and maybe it tries to get back up, and it just can't make it, and it comes back over here. It is a lousy DC pattern. But that's all that the IFC board needs to see to keep the gas valve on. It knows that there's fire. That's all we're asking. It's a very small current flow in microamps, and as long as we have fire and we have a circuit, the board will keep it on. So at this point now, we ask a class typically, well, what the heck is a microamp? And we say, well, what fraction of an amp is a microamp? And typically, the classes will always say, well, 1 microamp equals what fraction of 1 amp? So, Jeff, what does the class always usually say?
It's usually 100.
100? And then sometimes we'll even get better than that, and they say 1,000.
Yeah.
You say, well, no, it's not. Because even if we talk about 100, or if let's go back and talk about 1,000. I can relate to that one very easy. Remember when we had thermocouples? Those were 30 millivolt thermocouples. So a 30 millivolt thermocouple was 30 millivolts, which is voltage. And milli means 1,000. So a 30 millivolt thermocouple is 30 thousandths of 1 volt. That's a fraction. Okay. But micro, if micro isn't 1,000 and milli is 1,000, we're not talking about milliamps here, we're talking about microamps. 2 to 4 microamps as low as 0.2, 2/10 of 1 microamp. So a microamp is 1 millionth of 1 amp at 24 volts. Okay? So again, we're talking about a very small portion. So when we ask the contractor, the technician that's out there, what are your microamps? And he says, they're okay. How does his eyeball see microamps? You can't. You need an instrument. You need a digital readout. So I hope you understand that when you light that furnace, you're going to get anywhere from 2 to 4 microamps, and it even improves a little bit after 5 minutes of runtime. Okay? So let's do this. Let's go back and talk about the microamp reading. If 2 to 4 is typical, what could I put for microamps on startup? Give me a decimal.
Let's say 3.
Point.
2.
Okay. Let's say on startup we got 3.2, and it's a little bit better, Kevin, after 5 minutes. Give me something a little better.
3.6.
3.6. Excellent. A few times we had a contractor at a job site. I want to bring you back here. We had a contractor at a job site, and he says, in the cases of hot surface ignition, he says the hot surface igniter comes on, I get fire for about 5 seconds, and then it goes off. And I says, that means you're not reading microamps. And he says, well, I am. He says, I got my gauge hooked up. He says, I did it just like you said. I took the wire off the flame sensor, and because it's an amp meter, I took the one wire and I put it on the flame rod, and I put the other wire on the wire that was on the flame rod, and I lit it up. And that's in series, and that would be an amp meter. And he says, I started it up, and he says, I got 13 microamps. He says, this is terrific. But he says, it only goes on for 5 seconds and goes off. Well, that's your 5-second safety. The board is not seeing that. The board is not seeing microamps. So I says, well, if you had 0 microamps, I would say that you got a ground wire that is cut, or the furnace is not grounded. But I says, so now he goes over here and he says, and he's on, I'm going to put this on a scale. You really can't see the scale with the camera. But he says, I got 13 microamps. He says, I'm using it right now, right in front of the furnace. I got 13 microamps. And I said, really? I says, what scale are you on? He says, I'm on the microamp scale. I says, but which one, AC or DC? And that's the point. He had it on the AC. And for whatever reason, if you have no microamps, an AC scale will pick up all kinds of microamps when there's none. So when he went to flip it back over to the 200, well, in this particular one, it's 200 somewhere, 20 microamps. But the point is, when he went to the DC microamp scale, he got his 0 microamps. Okay? So don't get trapped with that. Use the right scale. And at the same token, this is the part of the class where we also talk about on your annual PM check. An annual PM check includes cleaning the flame rod. Ladies and gentlemen, if you talk to 5 people, you get 5 different opinions. I've talked to the manufacturers. We clean a flame rod with steel wool. We take clean steel wool and we clean it. It takes you longer to remove the flame rod from the burner area. You take that out and you clean it and you put it right back, but it takes you a few minutes to do that. If you're going to use sandpaper, I have a little bit of a problem with that. Of course, you can't use emery because there's oil in there. But they also tell me today that it's not good to use aluminum oxide sandpaper. And I think you might want to experience or experiment with that. Because if you're a refrigeration technician, typically you'll have nice sheets of aluminum oxide. And but I used to clean them with that. But again, I'm not sure how they clean. But steel wool, that is so easy. You can always carry a piece of steel wool with you. So clean them manually. Okay, we okay with that? All right, let's go on. We're getting there. We're winding down now. Let's take a look at, is the remote flame sense installed? Question number 29. The reason that question is in there because we had some furnaces originally that didn't have remote flame sensors, and in some cases we had to add them. That's the only reason that it's in there. So you could put down yes. Okay? Okay, we're getting there. Now, the next one is igniter ohms. So if you don't have spark ignition, we want igniter ohms. I would like you to go to your handout and turn over to page 96. Now, we can only go by the specifications that the manufacturer gives us. And all we know on our furnaces today from Rheem is that if we use hot surface igniters, typically we could have the specification, ladies and gentlemen, is down here. The Norton and the Starlight. And you have pictures of them up here, so you can identify them by picture. But they're giving you a specification. And let's use as an example the Norton 45 to 250. We're saying to you that if you check the resistance of that hot surface igniter, you'll be somewhere between 45 and 250. Now let's stop and talk about that a little bit. Typically off the shelf, if you were to look at one, you'd probably end up with about 110 ohms. That would be typical. But the point is, in the field, the hot surface ignition depends on voltage, of course. The higher the voltage, the hotter it gets and the shorter the life. But we ask you to check the resistance at room temperature. So one of the first things you do before you turn the furnace on is to unplug the hot surface igniter, put your ohm meter in there, and check the resistance. Now, again, different opinions of different classes. We're saying that the maximum is 250 according to the book. We're saying to you that if you measured 175, is that okay to leave in?
Yes.
Yeah. You know, and now let's say you measured it, and we know maximum is 250, and you measured 210. Is that okay to leave in?
Yes.
Yeah, according to what we know, right? But now let's say you had 241 ohms. Man, that's getting right up there, isn't it? Now the point is, ladies and gentlemen, this is where the technician's personality comes in. You know, is it okay to leave in? Boy, I sure wouldn't. I'll tell you, that's getting very close to burning out. And that to me says that that furnace is going to go out at 2 o'clock in the morning and I'll get the call. At that point, the technician's got two choices. If he says, Mrs. Jones, the igniter is 241 ohms, the maximum is 250. Do you want a new igniter? Typically the customer might say, no, I don't want to spend any more money. Or the technician can say, you're at the peak of where it's supposed to be, and it's getting very close to going out. Typical, a good reading would be about 100 ohms. You're at 241. I'm changing it, Mrs. Jones, so your furnace does not go out during the time that you need it the most. Okay? So we're all in agreement with that at this point. Okay? All right. So if 45 to 250 is good, or not good, if we're getting close, and we already talked about what is good. Kevin, I'm going to ask you for the reading on this, so let me go get the job site sheet. What can we put down that we checked with an ohm meter then on the igniter?
175.
Good. 175 ohms. Perfect. Okay? All right. We're getting there. Before we go on, I want you to open up your handout to page 53. Sometimes the customer says, well, my old furnace lasted for 30 years and nobody ever touched it. Well, then you can open up the training manual and read them this paragraph. Here we go. This is one of two paragraphs I'm going to read you. I'm a service technician and I'm well equipped to work on your furnace because it says here on page 53, the HVAC industry, like the auto industry, is faced with increasing government-imposed efficiency regulations. New and more sophisticated mechanical means for achieving higher efficiencies have been engineered. Gone are the days when all a person needed to work on an auto was just a wrench and a screwdriver. The same is true with heating and cooling equipment. The use of the test equipment is now more critical than ever. These are some of the tools that we showed you. Okay? Back at the toolbox, again, this is the tool case that we carry. In this particular one, absolutely, we have an amp clap that goes along with the meter that we have. Again, these are in case the contractor technician does not have the tool. We also carry a capacitor checker, capacitor analyzer. Very important today. Capacitors, checkers have to be used. So I'm just showing you some of the things, and I think I showed you the rest of them. So again, we're talking about $350 for the tools for heating. So again, different tools, different part of the business, huh? Okay. Now I want you to get your hand out and go to page 49. And the very first sentence, maintenance, when a customer says, why do you have to come out and check it every year? You can say, because the book says so. But it's because of our furnaces today. They're very complex. Look, it says, the furnace owner should have a professional service company check the performance and operation of the furnace every year. This ensures the furnace owner of receiving the best possible performance and comfort from the equipment. Okay? All right. So again, you have a couple of statements to back up the things that you tell your customer. Okay, now we're winding down. We okay?
Yes.
All right, let me, a little water. Okay, here we go. The last question. Question number 31. ESP. Remember external static pressure? Let me bring you back to the technical data tag, which wasn't that the second page?
Yes.
Mm-hmm.
And remember, it said 0.1 inches maximum external static pressure and 0.5. So you got two specifications there. Let me explain them now. You have to understand this one because we will ask you to do some checking if you're in some real trouble. We have, sometimes we have contractors that call us and say, darn you and darn your furnaces, and they're not that nice usually. They're worse than that. But they say, you're a piece of junk furnace, it just keeps overheating, it won't heat the house, and I've even taken the limit out and increased the value. So maybe, I don't know, maybe it had a 110 degree limit, or maybe it had a 140 degree limit, and they put in a 200 degree limit, whatever it is. Point is, you don't change limits. By the way, we always safety check a furnace. On our PM check, we always make sure that the furnaces are safe. By cycling the gas valve a few times, we do know that we are proving that we don't have a runaway gas valve. Remember, a runaway gas valve is a gas valve that electrically has no power to it, but mechanically it sticks open. So by cycling it a few times, we know that the mechanical gas valve is working. That's a safety check. The other safety check is to check the main limit. We always want to check the main limit because that's what prevents the house from burning down, gentlemen. The way we check the limit, and that would be one of the last things that we're doing, is we put a piece of cardboard where the filter is, or we pull the blower wire, and we let the heat exchanger sit there and bake, and as soon as the high temperature limit, or as soon as the high main limit gets hot enough, it's going to open up and the fire goes off. And that's the way you sell yourself and your company. If you ever want to show that to your customer, it works out terrific. Mr. and Mrs. Jones, did anybody ever show you how we safety check your furnace? You let them watch the fire, you say, see, I'm pulling the blower wire. Or I'm putting a piece of cardboard here. So if your blower motor fails, we know that the fire is going to go off. And you let them sit there and watch it with you. Boom, the fire goes off. You say, see, it goes off. Now, Mr. and Mrs. Jones, we both know that your furnace is safe. You have no runaway gas valve. You do not have a furnace that's going to burn your house down. And you also have no carbon monoxide spillage that's going to harm you. So those are safety concerns. But now let's get back to this ESP. But all of this relates to an overheating furnace. When we talk about ESP, we gave you the specifications. We said we got 0.12 and 0.5. Well, 0.12 is for a furnace without air conditioning. So if you have no coil and just a furnace, the external static pressure to the furnace is only 0.12. Typically, we are servicing with A coils in there, with evaporator coils. So the specifications that we're concerned about is 0.5. Let me explain external static pressure to you. Now, I am not an expert on ductwork or pressures, but I'm telling you the things that I have learned from the factory rep, because these are the things that he checks when he goes out in the field and the customer says you have a bad furnace and it overheats and you got multiple cracked heat exchangers. He checks for external static pressures. Oh yes, and also blower noises. If we got ductwork that is not adequate, that means our external static pressure is not good. We just said that 0.5 is maximum. We have to be moving enough air so we can have proper air conditioning, and also that we don't overheat a furnace and we have proper temperature rise. What I'd like you to do now is open your handout and go over to page 16. Now, on page 16 is a specification that is on blower cabinets. Today we have all kinds of blower specifications on them, and would be typical to this. So on the access panel you can see this. And on the left side of this chart it shows all of the model numbers. And let's just take for an example a 100,000 BTU furnace, because Kevin talked about 100,000 before. And we got two of them. We got one of them here that's got a 1/2 horsepower blower motor, and the other one's got a 3/4, and they're both the same size blower wheels. Well, up at the very top, it says blower speed, and let's just say it came set up for AC, and we were on medium high on both of them here, okay? So these would be blower speed, got 4-speed blowers. Well, also back to the top, it says CFM, cubic feet of air per minute, air delivery, external static pressure in inches of water column. So if you have external static pressure anywhere from 0.1 all the way up to 0.7, you can run down the column and see how much air you are delivering. So as an example, if you had the maximum 0.5 inches, which is the maximum that was on the data tag with the A coil. So again, it's set over here, maximum 0.5 inches, maximum external static. We have a specification for 0.5 inches. If you're looking for these two motors on this size furnace, and if you jump down here on the 1/2 horsepower, medium high, let's jump down here and see how much air we're delivering. See, 1105 CFMs per minute. If you got the 3/4, you've got 1845 per minute. Oh, I love this example. I think I picked out a good one. Let's just say you had a 3-ton AC. Okay? Now, a 3-ton AC, how many CFMs per ton?
400.
400. Means we can go from 350 to 450 though. But average of 400 CFMs. Do you think, if we had a so we're looking for 1,200 CFMs, aren't we?
Yes.
Do you think this is okay?
No.
Well,
It's a little light.
it could be okay because we
But it's a
could,
little light though.
but we could pick up a lot of latent heat. Could be a great dehumidifier.
Yes.
See? But if you wanted, whoop, there goes my pen. If you wanted to get closer to that 12, you could bump it up to the high speed. I'm sorry, you could bump it up to the high speed here, couldn't you?
Yes.
And now you got, what does that say? 1255, huh?
Right.
Now you got just a hair over the 12, and that's the way you adjust this. I mean, we're talking about specs, and I'm going to show you how to do this in just a minute. But look at this, if you had the 3/4 and you had the medium high, look at this! Look at that! Way too high!
5 ton, yeah.
Right! So in other words, you might not have a correct application. You want to have a correct match, but I'm just giving you this as an example. But you do not know what the CFM is unless you know what the maximum, or unless you know what the external static pressure is. If you can determine what the external static pressure is, you'll know how much air is going across that furnace. And that's what we're going to show you how to do. It's easy to read a chart, but you got to know how to do it. Okay, here we go. All right. Maximum external static pressure. You're going to use a couple of instruments. You're going to go back and use the magnehelic, and you're going to use a couple of Dwyer probes. And you're going to stick them in a ductwork. We're going to say to you that you're going to take one of these probes and stick them into supply, and another one you're going to stick into return. That's all. Let me explain a little more. We're saying that we want to use the magnehelic. Now, we showed you before that you have a positive on top and a negative on the bottom. So we want to stick a hose on the positive, stick it on the probe, and which is the positive ductwork? Supply or return? Which is the positive?
Supply.
Supply. Okay? So we want to take this and stick it into supply. So you're going to take this, attach it here, and your hose is going to go over here, it's going to go into your supply. The return, it's sucking air into the furnace, it's negative. So this one gets attached to the negative port, and we stick that into return. And all we do is turn the blower on. That's it. And the needle's going to go up because whatever pressure, remember, static pressure means that the air that's being pushed, produces pressure on the ductwork. It's measurable with an instrument, and we measure it in inches of water column. So it's a specification that we use in the industry. If we take a probe and a proper instrument and we stick it in the ductwork, we get a reading, and it's measurable in inches of water column. Now, the same thing on the return. If we are sucking air, it's negative, and it's also producing pressure on the ductwork, but it's producing negative. That's why when we oil can ductwork, when we blow in the supply, the oil can's outward, and on the return, it'll oil can inward. Okay? So positive and negative. But what are we still talking about? We're talking about static pressure on the ductwork. It's external static pressure. Let me make sure this is clear so you understand. This data tag said maximum external static pressure. Okay, let me shut this off. It's external to the furnace and nothing else. When we say external to the furnace, that means you take your probe and you stick it in the supply under the coil. That's external to the furnace. If we go beyond the coil, now it's external to the coil. And it won't give you the right reading. We want to know how much air is going across that heat exchanger. Because whatever's going across that heat exchanger is being supplied to the A coil. Okay? So the point is this, we stick this under the coil. Now watch this, how we use this. We take the static probe and we stick it in. If this isn't enough flow, we poke a hole under the coil. We stick it in with the point force downward. Because the air is supposed to hit the point. On the side of this probe are two little holes. So you get a Venturi action. Now you go to 5 classes, you get 5 different opinions about how to use this. I'm giving you the accurate one because I called Dwyer. I said some people say put it this way, some say put it this way, some say put it this way, and other people say this way. I say, what's the correct way? Because you're the one that makes it. They said this way, but I got to tell you, when I stick these things in ductwork and I get my reading, I turn it around and it hardly moves. But the point is, Dwyer says, let the air hit it this way. So now you understand. It goes under the coil, in the airstream. That's it. Now, the accurate way is to make your plenum look like Swiss cheese. You're supposed to put like a dozen holes. We don't do that. We're not asking you for that. This is going to get you close. Get it as best you can in the airstream and get a reading. So now you got it in, now this is in the supply. You take the other one and you get it external to the furnace into return. That means before the furnace, that would be before the furnace and after the filter. I think I'm saying that right. It's in between the filter and the furnace. So wherever you go, you get on the return side of the filter, on the furnace side of the filter, and you stick it in the airstream. Of course, if the air is coming this way and so forth, you stick it in there and point it like so. And then you say, well, I can't get there. They got electronic air cleaner, and I don't feel like drilling holes on that side and so forth. Fine. Go on the other side of the furnace and poke a hole in the blower compartment. You'll get a negative reading there. That's a good reading there also. If you can't do the other way, just get a hole in there. So now, what happens is you saw that this needle deflected. When I did a positive pressure, the needle went this way. When I did a negative pressure, the needle also went this way. Positive, negative, that means they will add. Okay? So, you could read 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Watch. The chart goes beyond the maximum. The furnace is designed for the maximum. It will still work at 0.6. It'll still work at 0.7. But now we start increasing velocity sounds and we start losing air. Let's see if that's true. Our first example was half horsepower, 0.5, and we had 1105, right? If we went up to 0.7, we got 1020. So you see right there that we start losing air. So if the ductwork is all choked up, we have higher external static pressure, and we start losing air, and we gain velocity sound, which again is overheating furnaces, blower noise, and so forth. Now, watch this. We'll come back here now. When you start looking at the modulating training manual, you're going to see furnace blower specifications that go all the way up to 0.8. But that's a different kind of a blower. It changes its speed depending on the static, but 0.8 is maximum on a modulating. But on a conventional furnace, and you look at all furnaces, they will all have the maximum external static pressure. Now, let me go a little bit further. We're going to ask you to take the external static pressure. I'm going to come over here. We're going to ask you to take the external static pressure if you call and say you're on your third set of heat exchangers, or even second set. We're going to ask you for a temperature rise. And what you're probably going to tell us is that you can't get a temperature rise because the limit keeps opening up and the furnace keeps cycling. So let me give you an example. A couple of years ago, I had a contractor, new housing installation, and he said, darn you, darn your furnaces. And he says, these furnaces will not heat the house. The houses aren't even completed yet. And I put in higher limits. He says, it keeps limiting, and I'm on the high speed. So I met him at the call. This was a call that I had to meet him at. It was kind of a PR, but to teach him how to service the furnace. His gas pressure, he says, I can't even heat the house, and I'm down to like 2 inches of gas pressure. How can you run a furnace on 2 inches? 3.3 is the bare minimum. So first of all, if he could keep it on, it would be condensing in his vent, if it's an 80 plus, and it would be condensing in his heat exchanger. But I said, let's check your maximum external static pressure, because that's going to tell us if your ductwork is correct. So I gave him a crash course with the magnet healing, explained it, brought out the charts and so forth. I says the maximum you can have is 0.5, 1/2 inch water column. Poked a hole in the supply, poked a hole in the return. Turned it on. We did 2 furnaces. And gentlemen, I'm not the ductwork expert, but I do remember his external static pressure on the first furnace was 1.2. The second furnace was 1.3. Way out of the realm of having proper ductwork. And again, I'm not a ductwork expert, but I looked at his ductwork, and he was way out in some of these suburbs, way out. Apparently, they don't have any code. His particular ductwork was all 100% supply and return, all flex. He used all flex, and it's a very high restriction. And I told him, I said, you can't run furnaces like this. I said, because not only will the furnaces not heat, you've lowered the gas pressure, you've increased your limit. I says, wait until the springtime, because I'm out here during the wintertime. In the springtime, you're going to be turning on the AC, and they're going to ice up. And I says, I know, then the technician's going to come out, and he'll say, I'll have to increase the pressure and get rid of the ice. And he grossly overcharges it, and then, of course, we start losing compressors. So it's not a furnace problem, it's not an AC problem, it's a ductwork problem. So keep in mind, if you call for technical assistance and say that we're going through a lot of heat exchangers, I have an overheating furnace, that's when we will ask you for an external static pressure reading. So let's go finish our last question on the job site. And that's question 31. If 0.3 is good, 0.35 is good, 0.4 is good, 0.5 is max, and we have a good operating furnace, and especially we have a good operating furnace that had a low temperature rise, we would have a lot of air going through this furnace. Jeff, what do you think we could put in here for external static pressure?
0.42.
Hey, look at that. See, he reads. In other words, it's on 0.4, but it's just a hair above the 0.4. So 0.42. Excellent. Wow. Okay. Are we okay with that so far? You know, gentlemen, I can ask you if you've got questions, but keep in mind we have people watching this on a video. We've done a lot. This is a crash course in heating. Well, we showed you I'm going to come back over here. We showed you what the job site was like, how to use it. We showed you how you can use it. You can use a lot of the information on a PM check, but you use it especially for troubleshooting. Now let me come back to the overhead. I hope you understand that we went through question 1 through 13, and we went through question 14 through 31, and the 90 plus did not apply, and question 17 did not apply, and I guess these did not apply. So what are we saying? Out of 31 questions on an 80 plus furnace, we didn't use 1, 2, 3, 4, 5, 6, 7, 8. We didn't use 8. So what does that leave us? 8 from 31 is 23, right? Those 23 questions. But hey, even if you're doing a 90 plus, it's all the same information, all the same diagnostics, same information. The only thing that's different with a 90 plus is to talk about your venting. This is how you diagnose in 20 minutes.